Hi everybody, so in this next part we're going to continue with our exploration of differential calculus and we'll cover some applications. So in particular what we're going to look at first of all is a trick known as implicit differentiation. So this is if you cannot compute the derivative explicitly but you have a relation between x and y. And then we'll look at velocity and acceleration as concepts that are grounded in physics but then have an interpretation using the derivative. And we'll finish off with a little bit about finding the minima and maxima of a function. So let's start with implicit differentiation. So what we've done up to this part is we've been given a function y equal to f of x, and then we've computed the derivative of that function. So we can compute derivative f prime of x. But however, not all equations are of the form y is equal to f of x. So for instance, if I take the equation of a circle, x squared plus y squared is equal to 25, I can write that as y is equal to something, but it's a little bit laborious. So let's do that first of all. So I have that y squared is equal to 25 minus x squared. Y is plus or minus the square root of 25 minus x squared. And now if I want to compute dy dx, I have to use my rules. So I can say, let's first do it for the plus sign. Dy dx of square root of 25 minus x squared is 1 over 2 times the square root times the derivative of what's inside the square root, so that's minus 2 times x, so this is chain rule, get minus x divided by the square root. And likewise, if you take the minus sign here in the specification for y, you get d dx of minus the square root. And then if you do the same calculation, you end up that this is plus x over the square root. So this is possible to compute the derivative, but you see it's not entirely straightforward. And implicit differentiation is a better solution here. So this is easier to compute with implicit differentiation. And what is it? It's a very easy trick. You just take the equation x squared plus y squared is equal to 25, and now you take the derivative of both sides, to get d dx of x squared plus y squared is equal to d dx of 25. And now we can work that out. So d dx of x squared, that's 2 times x. And now d dx of y squared, that's 2 times y prime, the derivative of y. And that is equal to 0 because the derivative of constant is 0. So here it's important that it's important to remember that y is a function of x. So when you take the derivative, you have to use the chain rule and first take the derivative with respect to y, 2 times y, and then times the derivative of y with respect to x. And so now we can rephrase it a little bit to say that y prime is equal to minus x divided by y. And oftentimes this is all you need. We'll see an example of that in a minute. But the important thing is that to note is that this is a quite easy calculation to do, and also it gives you y prime as a function of x and y. So now, how does that relate to the solution that we found earlier? Well, it actually gives the same result. Because if you take this relation that we had here for y, so y is equal to plus or minus square root of 25 minus x squared, and you substitute that in the relation for the derivative, you get y prime is x minus x divided by y, so minus x divided by plus or minus 25 minus x squared. And you can write that with a little bit of abusive notation as minus or plus x divided by square root of 25 minus x squared. So just to sum it up, with implicit differentiation, there's nothing much to it. You just take the relation between x and y. You don't try to invert it or anything. You just take the derivative of both sides, and then you work out what the derivative is. So let's do an example of that. For the example, we'll take the equation, or we'll look at the equation of the tangent line to the curve x squared plus xy plus y cubed is equal to 4. So, and this should be 2 times y cubed. 2 times y cubed is equal to 4 at the point p minus 2, 1. So the first thing to note is that this curve right here, it's almost impossible to write this as y equal to some function. Almost impossible to write this as y equal to something in just x. If that's the case, and you have to compute something with derivatives, it's useful to compute the derivative via implicit differentiation. And here, we're going to have to compute a derivative because for the tangent line, we need the slope to the curve. So let's start by computing the derivative. So we have x squared plus xy plus 2y cubed equal to 4. And now we take d dx of both sides. We get 2 times x. And now I get a product here, so I have to use the product rule. I get y plus x times y prime. So that's the derivative of xy, and then I get plus 2 times 3y squared y prime, and that is equal to the derivative of the constant 4, which is 0. So we can rewrite that a little bit to bring out the y prime, and I get y prime times x plus 6y squared equal to minus 2x minus y. And so y prime is minus 2x minus y divided by x plus 6y squared. And again, what you see is that you get the derivative, you get y prime as a function of x and y. And now you might say, well, how do I get rid of the y? Sometimes you can get rid of the y, like with the circle, sometimes you can't, but most cases you don't have to get rid of the y. So here we have y prime as a function of x and y, and there's no need to eliminate y. And why is that? Well, we want the slope at the point p minus 2, 1. So at p 2 minus 2, 1, I can just plug in the values that I'm given. So I get minus 2 times minus 2 minus 1, 1 plus 6 times minus 2 squared. And if you calculate that and you simplify it a little bit, you get 3 over 4. So we get the slope, the y prime is 3 over 4. And you see how easy this is, just implicit differentiation. Don't worry about eliminating y, it's not necessary because you only need it at a single point and you have the y value right there. And then to wrap it up, we can write down the equation for the tangent line. So we have that the tangent line has to pass through this point, so it's y minus 1 equal to 3 over 4 x plus 2, and we can simplify that a little bit to read y equal to 3/4 x plus 5 over 2, and you can clear the denominator if you want to write this as 3x minus 4y plus 10 equal to 0. All of these are correct. I think, let me just double check. So times 4, 3x minus 4y